In this talk, we look at the three families of components that create Apache Druid. Apache Druid is a fully distributed system formed around a set of loosely coupled Java processes that run in any Linux environment with Java Runtime. Query components get data out, you'll be glad to know. Data components ingest source data, and they calculate answers to statistical questions. Finally, master components do process coordination, tracking data in the cluster, and governing ingestion tasks. Let's start there. The first Java component is the coordinator. It choreographs, amongst other things, the distribution and balance of ingested data using replication as an availability tactic. And where does that data come from? The overlord is a choreographer, this time over all ingestion. Typically, you would run multiple overlord and coordinator processes, say by creating a number of master nodes. Then you get high availability and can do rolling upgrades. Here we meet our first dependency for Apache Druid, the metadata database. It contains system tables, including one that has information about the data that we have ingested. Just like with the overlord and coordinator processes, in production you'll probably want some resilience in whatever database system, say MySQL, you're going to connect Druid to. And while we're talking about dependencies, there's a second to be aware of, Zookeeper. That's what gets used for leader elections when I have multiple coordinators and overlords running, and it also provides facilities for inter-process communication and health monitoring between all of the components in the cluster. Again, as with the metadata database, think about building some resilience into that service as well. So, we have our Todrick halls. Who are the dancers? Let's start with the dance of ingestion. The dancers in the ingestion ballet are the middle managers. They spin up tasks, lovingly called peons, that ingest your historical data in batches or can take the very latest data direct from an event hub. Out of the box for ingestion, I have a lot of options: cloud, web, disk, and Hadoop, and there's default support for Kafka or Kinesis. As an architect, I might decide to combine my ingestion methods here because in a streaming architecture, I might need to backfill data, add late arriving data, augment real-time with high confidence data, or perhaps I'll want to append or overwrite data I've already ingested. Now we need somewhere to put this data. In Druid, we call that the deep store. That's our library. This is Druid's third dependency, and it could be, say, S3 or HDFS. Our data is optimized by each of those ingestion tasks. They take a row-wise structure that's great for writing into one more suited for OLAP use cases: columnarized, indexed, and compressed. As your timeline of events builds up, each portion is fully version controlled when it's written, with each version being immutable. The overlord only updates the metadata database when it knows that data has been safely and completely ingested. Great care is taken around this process. For example, exactly once ingestion is guaranteed for Kafka by carefully monitoring topic offsets. One of Druid's magical applications is for real-time data analytics, making data immediately available for analysis by our users. The tasks that the middle manager has spun up don't just ingest data, they also give immediate insight into your real-time data. Data being ingested from, say, Kafka is immediately queryable via those peons. We have immediate access to your business's short-term memory, and we can see that it gets put into a long-term memory inside Druid's deep store. But how do we go and look at that? Historicals copy data out of this long-term memory and make that available for querying. And it's the coordinator process that, seeing what's been ingested, instructs them to load that data according to the period of time we want available and the replication factor we want for resilience. What's great about this loosely coupled way of working is that the coordinator will automatically distribute data when you add new historicals. As my data grows, I simply add more historical processes, and the coordinator will automatically find them and push data to them, even rebalancing the data automatically. There's no need to go back into ingestion jobs and start connecting to new servers or anything like that. Another cool thing, the coordinator can be made aware of dedicated groups of historicals called tiers. We can target particular periods of time or particular datasets at those tiers to create a better cost-performance balance. Perhaps this new tier that I've added will have larger disks and less processing capacity. This self-awareness of resources also extends to ingestion. When there is more work to do, say I have larger data volumes, data arrives faster, or I need to do a big batch upload, I can add more dancers to the ingestion ballet. Now our overlord has more resources at its disposal and can keep up with even faster data rates and volumes. It grows as you grow. A good rule of thumb is that Druid achieves 10,000 events per second per core. I've seen 3 million events per second on a cluster by scaling out with more worker cores. Now, we can't expect our applications to know which of these many different sources of data to go to in order to get an answer. We need just one place to execute a query and to handle the complex job of combining these multiple sources of statistical results output by the historicals or the middle managers. That's the job of the broker. It carefully plans and distributes work to the data it needs, consolidates answers, and does any post-processing required. I can ask the broker to execute timescan, group by, and top-end queries via an API, even text search, either in JSON, which gives me the most control, or in SQL, powered by Apache Calcite. That has two benefits. One, that I can plug in any application that supports SQL over JDBC, like Tableau, but secondly, that it has enabled rapid development of Druid SQL support. New in Druid 0.18 are query lanes. That means that in configuration or programmatically, I can determine if a particular query should cut to the front of the line, or, as we'd say in the UK, jump the queue, and be executed ahead of other queries. We talked about redundancy of the master processes. Well, you're likely to need that here as well. Perhaps 2 broker processes fronted by a load balancer. But you also need to think about the number of queries that are likely to be running at once. In the wild, we usually see 1 broker process for every 10 or so historical processes. Let's turn now to look at how queries actually execute. When the query covers data that's arriving in real time, the broker crafts tasks for those middle manager peons, asking them to calculate the necessary aggregations and pass them back. Middle managers are very likely to have the data in memory. Perhaps it's just arrived, for example. And for any data that's in this artificial brain's long-term memory, stuff that's older, it does the same thing, but this time to historicals. Now, the historicals have this on disk. Remember, they were told to load this from deep storage by the coordinator. But when a query executes, it loads it into memory and processes it there. Then it keeps it mapped for later use, meaning your most commonly run queries run at blistering speed. Also, in both the historical and the middle manager processes are in-memory lookups, key value pair tables that enable us to enrich data as it's ingested and when it's queried. A note that in a fast and big database system like Druid, we need to be sure that at all times the answers we get are reliable, and it's the broker that has responsibility for making sure that happens. It seeks out the right versions of complete periods of time, issuing tasks to the right parts of the cluster to give you the very latest data. Note the isolation of the analytical tasks that the broker initiates on the data services. They are each distinct pieces of work, meaning there is no cross-node chatter, and because data is immutable, there's no row locking, no recalculation, and no redistribution of data. And Druid can also cache results along the execution workflow confidently. Druid also has had native support for Apache data sketches since, well, forever. They can be used to speed up distinct counts and set operations and the calculation of percentiles by using approximation. Not just opting to use them dynamically as queries execute, but also to put them in place proactively at ingestion time. And since Druid 0.19, group by and time series queries make use of query vectorization, a neat trick that adds further parallelization to the process inside each of the machines themselves. This highly parallelized query process is very fast, very scalable, and very resilient to failure. Results typically come back in under 400 milliseconds. That's why Druid powers modern data applications used by many thousands of people concurrently. And this ability to query data live as it streams into Druid enables your business to finally realize that dream of adding real-time data to the reports and dashboards you have today. Druid supports TLS for encryption of data in motion, and of course you can apply encryption to the dependencies in the usual way. And Druid also emits all manner of observability metrics and logs that don't just expose the health of Druid, but, because of that real-time data you get, of any system producing data that goes into your pipeline. Druid was built with extensibility in mind from day one, so you can find all sorts of extensions outside of those in the core distribution, whether that's different types of deep store, metadata database, or query language. This is Druid then. 3 dependencies: Zookeeper, the deep store, and metadata database. Then we have overlords and middle managers choreographing ingestion, not forgetting that middle managers also respond to real-time queries. And then we have the coordinator and historicals making long-term data available. And finally, the broker, giving us super fast and reliable statistical data from both short and long-term memory. You can learn a lot more about each of the components in this talk by having a look at the official documentation at druid.apache.org. And if you have any questions at all, come and say hello to us in the Druid user forum by Imply, meet us in a Druid meetup, join the Druid professionals group on LinkedIn, or follow Druid.io on Twitter.